Alright, gang, here we go. This is for Chem 2 Unit 11. We're talking about Ka values. We're going to do some ice table here. So last video we talked about weak acids, Ka, so on and so forth, and we talked about how to calculate Ka from equilibrium, from like a pH, right? So now we're just going to work the backwards way. This is very, very similar to the ice tables you're already familiar with using. Here's your general setup. You'll notice that it's almost exactly the same. Write the chemical equation, write the equilibrium constant, set up an ice table, and then set everything up as a function of the change that x value. Substitute into the equilibrium, and then Bob's your uncle. Life's good. All right, so here's an example. It says calculate the pH of a 0.3 molar solution of acetic acid at 25 degrees Celsius. So here's your balanced chemical equation. All right, here's your equilibrium expression. Notice water's not there because it's pure substance, doesn't affect our equilibrium. All right, and then they've set up our ice table. Initial, change, equilibrium. Here's your acetic acid, hydronium, and acetate. All right, our initial concentration was just that concentration they gave us to start. So there's your 0.3, and there was no hydronium or acetate to start. All right, now this is all in a one-to-one relationship, so when this goes down by some amount, your hydronium and your acetate will go up by some amount, and they're all going to be equal to each other, and so then you've got this, this will be equal to 0.3 minus x, and this will be equal to x and x. So now all we have to do is just take these values and plug them into our equilibrium expression. So here's our equilibrium expression, so it becomes x squared over 0.3 minus x. Okay, now they make a new assumption here that we haven't really talked about. They said if we assume that x is much less than 0.3, then 0.3 minus x becomes just 0.3. This problem becomes much easier since we don't have to use the quadratic formula to solve it. Now, the assumption that you can make here is because there's such a big difference between the Ka value, this Ka value to the negative fifth, and this is only in the tenths place. These are more than 2 or 3 decimal places away. Like, let's run with 3 decimal places away from each other. So we can assume that we can neglect that x because that change isn't going to be enough. So then this math becomes really, really easy. All right, and we can just say, well, it's just equal to 0.3 times this value, take the square root of it. X is equal to this. So that's our concentration of hydronium, because that's what our x was right here. And to find the pH, we just take the negative log of that value, and you get this. This is your pH right there. All right, so just by given the starting Ka value of or the starting concentration of acetic acid, we were able to calculate the pH. Pretty powerful tool, all things considered. Now, if you don't, if you're like looking at this and you're like, well, I'm not sure if I can neglect the x or not. The only thing that it hurts is maybe you'd have to do a quadratic formula to solve your problem. But other than that, like, just run with it, see what 2 answers you get. See if it actually turns out to be different. All right, let's do a practice problem here. It says, what is the pH of a 0.40 molar solution of benzoic acid? The Ka value for benzoic acid is given in this table, and I already grabbed it for us right here. So we're just going to call this HBA because I don't want to write out all that. It's going to mix with water. Okay, and at equilibrium, we're going to form H3O plus Ba minus. All right, so we got an ice table, ICE. All right, and so our initial concentration of HBA, benzoic acid, excuse me, is 0.4. This is negligible, or this doesn't affect our equilibrium, so we're not even going to bother with it. We're going to start with 0 of this, 0 of this. It's always going to start like this. This is super easy, right? Concentration of your acid, 0, 0, ignore the water. All right, this is going to go down by so much. Now you have to pay attention to what's the change. Now, so far, we've only really talked about losing 1 proton, so it's always been a one-to-one relationship. In the next video, that's going to change, but for now, let's embrace it. All right, and we're going to embrace it. All right, and this would go up by some x, this would go up by some x, so this would become x and x. So our Ka is equal to, well, it's equal to 6.3 times 10 to the minus fifth. All right, now notice that this times 10 to the minus fifth is much, much, much smaller than this 0.40. It's 1,000 times smaller, so that means we can neglect this x, all right? So what this becomes then, well, this on top will be our hydronium concentration. All right, this will be our benzoate concentration, and down here will be our benzoic acid concentration at equilibrium. Okay. Now we just established that we can ignore that x value right there, so this simply becomes x squared over 0.4. So if we solve for this, that means our x value, we need to take 6.3 times 10 to the minus fifth times 0.4, and then take the square root of that. All right, we get 0.00502. All right, how many? We only really need 2 sig figs, so it would be 0.0050, but whatever. So that's our concentration of hydronium. So to find the pH, our pH is just going to be equal to the negative log of that concentration, 0.00502, etc. All right, so our pH is going to be equal to negative log of the concentration. So 2.290. All right, but this has, let's see, this has 2 sig figs, and so our answer would round to 2.30. All right, and thank goodness that's an answer that we have available to us, so that's got to be the right one. So that's pretty easy, right? It's just a nice table. It's really, another idea that, or a reason like that would stick out to you that you could neglect that x is because when we solve for this x, look how far away these are. If you tried to take a 0.40 minus your 0.005, you'd end up with just 0.40 again, because this, this subtracted is going to be 0.39, shoot, 5, and which would round up to 0.40 anyway. Okay, so that's kind of why we can neglect that x when they're small enough or big enough difference between the two. All right, last little bit. This is just another way to think about strong versus weak acids. Okay, we know strong acids, their concentration of the hydronium at equilibrium is equal to the initial concentration of the weak acid, right? This is because they completely dissociate. And we know the weak acid, the hydronium concentration will always be less than the concentration of the weak acid initially. All right, so really this creates a very different amount of conductivity and rates in chemical reactions. So here they've got a 1 molar HCl in this test tube, and then here they've got 1 molar acetic acid. Now you can notice here that this reaction with the hydrochloric acid reacts much more fast. Look how little magnesium is left in this test tube compared to here with the acetic acid. Here the reaction is completely gone, but the H2 is still being formed. Eventually they reach the same point, but that reaction rate is much slower in the acetic acid because it is a weak acid. It dissociates a lot less slowly. There's a lot less of it in this solution at any given moment. All right, next video we'll talk about polyprotic acids. Life gets more exciting then, but for now just practice those ice tables. Let me know if you have any questions, and I'll see you on the flip side.